It's here, I guess.
OK, awesome. Move that way.
All right, folks. Hello. Today we'll talk about the enhancing the protocol security with zero-knowledge oracles. And my name is Victor. I'm a Lido protocol contributor. And my co-speaker today, Eugene, he will tell you about the technical details about the ZK oracle in the second part. But before that, let me set the stage for that and explain the problem and set the solution framework. In the beginning, just a few words about the Lido, in case you don't really know about. Sorry. That's, yeah. So it's a middleware connecting the users with ETH to the node operators. It's more than 9 million ETH at the liquid staking. For this protocol, there are some important properties of Lido, like the ERC20 fungible token. We have also, in Lido, there is also permissionless withdrawals. So everything that's staked could be withdrawn if it's needed. And also there is a flexible staking router, which allows to set different validator subsets. And the most important thing is DAO voting, because every change to the protocol actually has to go through the DAO voting. And so the problem statement. For the protocol, it's needed to have some external data to proper count the value of the Steve token and to distribute the rewards across the stakers. And the essence of the problem is this external reported data should be minimized. The trust to this data should be minimized, or it's better completely removed. And to explain you the implementation for that, I need to talk about two main things. It's a Lido Accounting Oracles Committee and Oracles Report Sanity Checker. The first thing is a committee. So the Steve rebase happens every day with the Oracle report. Oracle brings the values like a consensus layer, validators balance, withdrawal vault balance, some other data, and it's recalculate the value of the token. It's kind of protected with a committee of 9 independent oracles, and only if there's 5 identical reports received from 5 different oracles, this data can come through. But not really yet, because there is a sanity checker in between, because there are some checks to basically tie hands for the system if there is a kind of abnormal or abrupt balance change coming. That prevents some possible attack vectors. However, in the previous implementation of the sanity checker, there is a problem. That's the negative rebase parameters was too limited. It was about like setting X% negative rebase per day. That is not really enough. So the solution is described in Lido improvement proposal number 23. And it consists of 2 main parts. The first is the stricter sanity checker. So basically, we decrease the limit of 5% of the consensus layer validators to 3.4 over an 18 days window. It's a major improvement because it's limiting the possible negative rebases. But the most interesting part, that's a pluggable second opinion oracle. And based on the Succinct Labs ZK Oracle implementation, based on the SP1 ZK VM, it provides this trustless verification for this data. It's calculated data from the external and provides the zero-knowledge proof for that data as well. And this kind of guarantee are the better results because we can consult the second opinion before we can do the rebase. So basically now I'm passing the mic to Eugene to explain you the technical details about the ZK Oracle.
Thanks, Victor. Hey, folks. I guess I'm the last thing between you and lunch, so I'll try to not take too much of your time. So yeah, let's dive right in. So just a quick update of how the problem translates to the technical part. Basically, like Ethereum have 2 layers, as you all know, and they're pretty much isolated, right? So there's like only like a few windows from execution layer to consensus layer, and in the opposite direction. And that actually brings a challenge, because all of the data that's needed for the Oracle report needs to be existing in execution layer, but all of the data is on the consensus layer. And normal solution is, as Victor mentioned, there's a Lido Oracle and a committee that brings that data from the consensus layer to execution layer, and it's a pool Oracle, and everything is fine, except it still requires building, and when you build an Oracle, there's still some challenges, right? Because majority vote-based Oracles still have this like attack vectors. One is simply brute force. You can still overtake 5 entities and then put whatever report you would like. The second one could be like slightly more subtle, called supply chain attack, because practically your Oracle is still an executable code. It has dependencies, and if some of the dependencies are compromised, your Oracle could be compromised as well. So if you remember that famous thing about left pad on NPM, if the guy didn't just rage quit and deleted it, but put some malicious code into it, pretty much like entire internet would be infected. And obviously there's still implementation risks, right? Everyone's like so far all developers are humans, and humans make mistakes, and if one of the mistakes is slip in, that would open an additional attack vector for compromising an Oracle. And here's where zero knowledge proof come. Technically, all of that data is publicly available, so like completely on-chain solution is possible. The only problem is that you would need to put entire beacon state, which is the data structure that captures everything on a consensus layer. You would need to put it on execution layer, and last time I checked, it was something like 230 megabytes SSD serialized, and it probably would be even bigger ABI encoded. And run hashing, SHA-256 hashing over, to produce Merkle roots for all of the validators. That alone would take something like 3 million hashes. So basically, overall, this is not feasible, because it will exceed any reasonable gas limits. And ZK actually helps with that, because straightforward use of ZK solution is to conceal some knowledge and produce a proof that you have it. The thing is that this knowledge does not have to be private. It could be publicly available. It's just you don't want to push all that data to the verifier to do the thing. So instead, we can just push the report itself, plus a proof that the report was computed honestly and consistently. And that reduces the amount of data and amount of computation that we need to do on execution layer a few orders of magnitude, if not millions of times. OK, so charting course on the technical approach. So as I mentioned, producing report starts with actual correct algorithm, right? In order to produce a report, you fix how this raw data that we have on the beacon state converts into a report. And this is actually an excerpt of the actual code we have. Most of the complexity is hidden behind, how's this? Behind this prepare input thing. But other than that, it's just basically this. And correctness and honesty requirements for producing the report is guaranteed by the ZK infrastructure itself. And we'll touch on this slightly later. The second part of the equation is actually having the correct data pushed into the both proof and verifier contract on chain. The tricky part here is that the this kind of like integrity guarantee is not, like, cannot be provided by the ZK solutions alone. And and practically, when we're like pushing final report and approve to the execution layer, we need to like compare something in the report with something on the blockchain that we can use to confidently check that the report was computed correctly. And we'll touch on what that something is in a few slides. And finally, if we have like correct algorithm and correct data, that guarantees that the actual execution report, actual report would be correct. Yeah, and the tricky part is that like when we're talking about this, like in ZK circuit or ZK program, 95% of the time actually spent on like proving all the data that we can actually ladder up to something on the blockchain that we can verify against. Literally, like the algorithm for Lido report is like for all validators, if validator withdrawal credentials is not Lido, skip it. If it's Lido, add the balance, increase the counter, that's it. This is your report. So practically like 15 lines at most. But proving the data is kind of like, oh, we'll get into it. So here's the thing. We need to prove a lot of data about validators, their balances, activation, exit epochs, et cetera, et cetera. But on the execution layer, the only thing we have is the beacon block hash. And this is actually was added, I'm not sure in Capella or Deneb, but pretty recently. So there was like EIP 4788 that brought this precompiled contract that keeps track of the beacon block hashes on the execution layer. And down it goes. So the next layer is that like beacon block hash is produced from parent root, state root, and body root, and a few other fields that are like in a beacon block header. And then state root is a Merkle tree root of the beacon state data structure that has like something like 30-ish fields. Basically, like this is like entire beacon state, consensus layer state. And the most important for us is validators root. This one is kind of like tricky because we'll touch on this in the later slides, but it's kind of like a Merkle tree of a variable list that actually have 2 to the power of 40 elements. Only like 1.6 million elements are actually used, but there's a trick that makes it important. And then for validators root, like that root is computed basically from a Merkle hashes of every validator, and Merkle hash of every validator is actually produced from Merkleizing all of the fields of that validator, and that's how it comes to be. And then there's also balances root, because like we're practically reporting on a consensus layer balance for all of the validators. And for balances, it's slightly different because they are packed in SSD spec. Balances are 8 bytes, and they're packed 4 items together into like packed balance, and then this forms leaves of the Merkle root, of the Merkle tree. And if you look at it, this whole thing looks like this. And if you don't know who this guy is, he's a Baron Münchhausen, a fiction book character, like main character in the fiction book. And he was telling like cool stories, like once he was traveling and got into a swamp, and he pulled himself out of the swamp by his hair, including himself and a horse and so on and so forth. And in fiction book, you can do pretty much anything. In reality, we're bound by some laws of physics and mathematics, and it wouldn't be possible, but there's a hook that we can use later that allows us to perform tricks like this. Just to touch on the technology side of things, so this whole thing is built on the Succinct Labs SP1. SP1 stands for Succinct Processor. And like this is the slide from their initial announcement half a year ago in April or something. Obviously, the benchmarking values might have changed since then. But like the part that talks about like developer productivity, I can literally I can definitely get behind this 100%, maybe 100 times, maybe even bigger. Because the best part of it is that it allows writing ZK circuits in Rust, and it's like a plain Rust, everything is supported, even like third-party packages, with some tricks that, with some caveats that I'll talk about later. And thing that I love the most about it is that both Oracle, like off-chain code, and ZK Circuit can actually share code. That allows for like a lot faster iteration. You don't have to fire your ZKVM emulator every time to test everything. You can actually do a lot of unit testing, a lot of integration testing, and that speeds up the development a lot. Yeah, and one thing worthy of mentioning is that there's like a bunch of like performant precompiles for pretty much, well, at least main crypto primitives like SHA, Ketchak, et cetera, that actually makes it run a lot faster even on ZKVM itself. Cool. So initial solution, I put a little bit of code on my slides. I think it should be readable, but if anything, I'll still talk through it. So this is basically entire code of the Oracle, except like it hides some complexity in the library codes. So basically what Oracle is doing is that it reads the consensus data, and it orchestrates creating a proof and submitting it to SP1 prover network, or SP1 prover if you're running locally, and finally just submits the report and proof to the contract on chain. This is also like almost like a full listing of ZK program. I just removed the parts that are not really interesting. So again, it's written in Rust and compiled into ELF. I forgot how it's abbreviated, executable linkable file or something, for a RISC v32 virtual machine. And like running this ELF on a virtual machine produces the AIR, algebraic intermediate representation, AIR trace that is later compressed into a proof. And this part provides part of the correctness guarantee, right? So this encodes the algorithm, and I'm not 100% sure how it happens, but practically the code in your solution is part of the verification key that will be later used for verifying everything. And even if single byte change, you get a new verification key, and you've got to redeploy your contracts or update or do some stuff. And that's part of the protection from malicious attackers, that only the blessed verified algorithm can actually produce proofs that will be passing on when we do verification. Yeah. And as I've said, major advantage is that almost any Rust code can be used, and I guess we'll touch on it in a few slides. So final piece in the grand architecture is the contract itself that accepts reports and verifies them. So the most important part of what it is doing is anchoring the data that we're sending to a blockchain state. So most of the thing as I've mentioned, most of the operations that the ZK is providing is taking beacon block hash and proving that, okay, we had actual state root from this given slot on a blockchain. Then, okay, we have state root. Let's prove that we had validator hashes. We have validator hashes. Let's prove that we had all of the validators and all of the data is correct below that. But finally, this whole tree anchors on the beacon block hash, and that provides us the hook that we need to pull ourselves out of the swamp. And second part is that it just verifies the proof. So contract literally just sends it to an on-chain verifier that can verify the proof, rerun those mathematical AR trace, algebraic intermediate representation, rerun it and confirm that yes, all the constraints match, all the data that was passed in it matches what we expect to see, everything's fine. And this provides the second part of the correctness guarantee and cements the solution altogether. And finally, just stores the report, nothing fancy, just record it into a mapping and make it available for later consumption by the protocol. A couple of challenges. And I think we're running out of time, so I'll run really quickly. One of the things was that like RISC-V32 is a 32-bit machine. And if you remember, number of validators in the beacon state is actually 2 to the 40th. And 2 to the 40 is actually, like, if you try to convert it into unsigned int 32, it will overflow. And one of the crates I used to build the tree hashing, this is actually tree hash. I'm not sure if it's from Lighthouse, from Sigma Prime, or one of the derived ones. By the way, kudos to Sigma Prime for open sourcing all that stuff. It will just basically overflow at some point, and everything will crash. So to kind of like overcome this, I had to kind of do a conditional execution, conditional compilation. So this is like for your normally x64 machine, and then this is kind of like equivalent implementation on RISC-V32 that doesn't hit that problem. There's a little bit of trade-off that we're kind of like artificially limiting the number of validators to 2 to the power of 29. But that's kind of like will sustain us for like 40 years from now, taking into account the current validator count growth. So should be fine, more or less. And the second part was that like kind of like naively generating the proof was extremely expensive in terms of like RISC-V cycles, and that impacts the cost of the proof, and that impacts the time that takes to generate the proof. Overall, it was kind of like something like it would took 1 hour for 10,000 validators, and it was kind of like scaling linearly. So for like 20,000 validators, it would be 2 hours, and like for 1.6 million validators, it would be like a couple of weeks, and that's obviously not practical. So what we had to do is to kind of like do some caching, and there was like kind of like 2 options. One option was to leverage the recursive proofs that SP1 provides, and kind of like store them somewhere. And if nothing has changed in that part of the tree of the recursive proofs, just reuse them without regenerating. The second approach that we took is actually storing this Lido validator state structure on kind of like on chain through Merkle root as well, and kind of like only recomputing something that's changed, that is basically like this validator delta. Cool. Final slide. At this point, we have deployed to Sepolia. We've run very extensive user acceptance test, verified that it works correctly for happy cases, verified that it rejects the proofs for a lot of like data tampering attempts and anything I could think of putting my hacker mindset. Things left to before we can launch is basically to complete the LAP23 compatibility. There's like a couple of things that we had to push back a little, and perform audit, and basically like put it for a DAO voting on Lido. And future enhancements, there's like multiple things we can support with like multiple withdrawal credentials. We can support, like we should support Pectra at some point, and all the future updates. Precise validator match, there's like a few heuristics that we're employing, and cost and performance optimizations. And yeah, I guess we're done here. Thank you all for coming. We can take questions if you have. Oh, sure.
All right. Thank you, folks.
Thank you all.